There are many different substances, each a combination of some of the 92 known chemical elements. Just as yeast, flour, salt, sugar, and shortening are the ingredients used in making bread, so are the 92 elements the ingredients of all matter. And if one of these elements is reduced to its purest, final form, its smallest unit would be an atom. No one has ever seen inside an atom. However, we think of it as a system of electrons circulating around a heavy nucleus at almost inconceivable speeds. In order to explain the principles with which we are concerned in this story, let's assume that we can stop the action within the atom. And further, let's acknowledge that this is a symbol representing the atom and not an attempt to show it as it actually is. It is impossible to show the correct relative proportions of an atom on this screen. For example, if an atom could be as large as the United States, one of its electrons would be only about 100 feet across. Therefore, to tell our story, we must resort to a symbol. Then we can think of the atom as being a group of relatively light, small particles arranged around a heavy nucleus. These are particles of electric energy. The lighter ones, the electrons, are negative electric charges. And the heavier one, the nucleus, carries positive charges. Normally, a state of balance is maintained within the atom by a positive charge in the nucleus equal to the total negative charge of the electrons. And when the atom contains its normal number of electrons, it is said to be in electrical balance, to be in a neutral electrical condition. It is possible, however, to disturb this normal balance, whereupon the unbalanced atom assumes an electric charge. Too many electrons will produce a negative charge. Too few will throw the balance onto the positive side. In order to visualize better the effect of this, let's introduce a color code in which the positive charge, or an absence of electrons, is represented with red, and the negative charge, a predominance of electrons, with blue. Then an object that is in electrical balance will be purple, an equal part of each of the positive and negative charges. We have been concerned so far with the electrons within individual atoms. Now let's see what happens when two or more neutral atoms come together. The outside electrons will no longer move exclusively within their original atoms, but will circulate about both atoms at once. And if we bring many such atoms close together, as in a piece of metal, then many electrons detach themselves from their original atoms and move freely throughout the metal. As long as the metal has its normal number of electrons, it is electrically neutral. But like an individual atom, it can lose some of its electrons and become positively charged, or it can pick up more than its normal number of electrons to become negatively charged. The electrons always try to get from a negatively charged body to one that is positively charged in relation to it. And if they're brought together, the electrons will flow from one to the other until both objects are equally charged. The establishment of unbalanced charges in matter is, in all instances, the principle of the generation of electricity. To illustrate further this principle, let's analyze the action within a cell, a simple source of electric energy. A piece of zinc is suspended in a suitable container. Its atoms are neutral until a chemical solution is added. Then some of the zinc atoms go into the solution, leaving a few of their electrons behind in the metal. The zinc becomes strongly negatively charged. Now a piece of electrically neutral copper is put in a chemical solution in another container. The copper will become very weakly negative. Since the copper has a smaller negative charge, it is positive with respect to the zinc. And if the two metals are connected, the electrons will surge from the zinc to the copper, and the charges will become equalized. This momentary current has little practical value. However, if we now connect the solutions, the charges in the solutions will become equalized, and the metals or terminals will be charged. We will then have an unbalanced condition of the electrons in the metals capable of producing a continuous flow of useful electric current. All of the work performed by electricity requires a flow of current. So let's see what principles are involved when current flows. There are three related to the flow of electricity. They are pressure or voltage, current intensity, and resistance. First, let us consider pressure. With nature always trying to maintain an electrical balance, there is a tendency for any negatively charged object to throw off or repel its excess of electrons, and for a positively charged object to attract electrons. This urge to maintain an electrical balance is potential electric energy. Electrical balance is potential electric energy. And since this potential energy is a repelling and attracting urge caused by opposite charges, its force or pressure is equal to the difference in the charges. It is called the difference in potential or potential difference. The unit of pressure or potential difference is the volt. The voltage, then, is always the potential difference at the negative and positive terminals of the source of the electric energy. It represents the difference between the number of extra electrons at the two terminals. And when a suitable path is provided, the potential difference causes the electrons or current to flow from one terminal through the conductor to the other terminal. To explain how this works, let's review the action of the atoms and their electrons in a piece of metal, where we saw swarms of electrons moving freely in all directions about the atoms. Substances in which this takes place are good conductors of electricity. If an outside electric pressure or voltage is applied to a conductor, the electrons will move predominantly in one direction. The effect is that electrons move from the negative to the positive terminal. This is the electric current. The unit of electric current is the ampere. 1 amp, now hold on to your hat, 6,300,000,000,000,000,000 electrons passing any given point in 1 second. Current, or amperage, then is the number of electrons that pass a given point in a given time. And now the third factor, resistance. This factor is controlled by the nature of the material through which the electrons flow. Again, going back to the motion of electrons in a metal, we said that they moved freely about and among the atoms. However, even in the best of conductors, some of the electrons collide with the atoms, tending to retard the movement of the electrons. This is the cause of electric resistance. Collisions are more probable in some metals than in others. Therefore, different metals offer different degrees of resistance to the flow of electrons. For example, copper has low resistance, It permits the electrons to flow freely with few collisions and is therefore a good conductor. Iron offers more resistance than copper. Collisions with the atoms are more frequent. In some substances, no electrons are free to move around as in the metal. All of the electrons stay with their atoms so that no current can flow. These substances are the insulators: glass, porcelain, rubber, and many others. The collisions that the electrons have with the atoms set the atoms into more violent vibration. This makes the metal hotter. If there are enough of these collisions, the metal will radiate heat and light. Heat and light from electrical sources, then, can be obtained as the result of resistance in some metals. The unit of resistance is the ohm. Its value is best understood when its relation to the other factors is explained. A pressure of 1 volt produces a current of 1 ampere through a resistance of 1 ohm. Whatever the source or the magnitude of electric energy, these factors always have the same relation to each other. So, in order to supply our great demands for electric power, we must have facilities for generating great currents at sufficient pressures to overcome the resistance of the lines, as well as to do the work. Power for industry, transportation, and light, as well as for many other conveniences we use in our daily lives. Our own sources of current able to perform these amounts of work are the electromagnetic generators. In order to explain the manner in which electricity is produced by electromagnetic generators and used in most electrical machinery, let's have a look at magnets and magnetic fields. The Earth itself is a magnet. So are the tiny electrons. All of the electrons in any object are tiny magnets. When a predominant number of these tiny magnets point in one direction, we have an extremely small magnetized block called a magnetic domain. Magnetic material, that is, material capable of being magnetized, is made up of such domains, pointing in all directions. When these domains all point in the same direction, we have a magnet. In some materials, such as copper, the tiny magnets of the electrons never line up. These materials are non-magnetic, cannot be magnetized. Every magnet has a magnetic field. Magnets may be made in various shapes to provide convenient and strong fields. To understand how a magnetic field is useful in the generation or application of electricity, let's go back to the electron, Mr. Electron, and watch him move across the magnetic field. Will you do it again, Bud? Now notice, as he enters the magnetic field, he's deflected from his original course. His deflection depends upon his velocity. Now, as we have previously shown, conductors have many free electrons. And if a conductor is moved across a magnetic field, the mechanical action causes the electrons in the wire to be deflected, just as we saw Mr. Electron deflected. This, in effect, establishes a negative and a positive charge at the ends of the conductor. we now have two charge terminals capable of producing a continuous flow of electric current just as we had in the cell. This is accomplished in practice by providing a means of continuing the movement of a conductor within a magnetic field. In all electromagnetic generators, regardless of size, the same principle is used to generate electricity. The deflection of electrons in a conductor moving across a magnetic field. The same magnetic fields and forces are also used in making an electric current perform useful mechanical work. Remember that an electron moving across a magnetic field is deflected. If the electron were moving in a wire, as when electric current flows, the deflection of the electron would cause it to push against the wire, tending to move the wire. Billions upon billions of these tiny pushes combine to provide the force. The stronger the current, or the greater number of electrons, the greater the force moving the wire. These forces on current-carrying wires in magnetic fields furnish the power for all electric motors, from the simplest to the most complex, from the smallest to the largest electric motors. The principle is the same. The deflection of electrons flowing in current-carrying wires by magnetic fields. In fact, interaction between the magnetic fields and the electrons is the basis of all electric devices. And now we may summarize that the billions and billions of atoms of which the universe is built are composed of positive and negative electric charges. That these charges are normally balanced in matter. That by unbalancing these charges, electric energy is made available. That the urge of nature to restore this balance creates electric pressure. And that the response to this urge, the action of the restoration of the balance, is a flow of electric current. The flow of electric current, then, is simply movement of electrons away from objects that have acquired a negative charge to objects whose charge is relatively positive. It's this principle that has made possible the countless electric devices which contribute to the comfort and fulfillment of richer and happier living today. Devices which will expand that to unlimited horizons in the future. Devices whose operation is dependent upon nature's design for matter, demanding
Western Electric, 30 years ago, before solid-state electronics and transistors. From factories like this came a nationwide switching network connecting millions of telephones. If only two phones existed, only two wires would be needed to connect them. 10 phones would require 90 wires to reach each other, if no switching means were available. The 85 million phones in actual use today would need an astronomical number of wires without an adequate switching system. The switching network built by Western Electric includes over 10,000 major switching centers, that enable any phone to reach any other phone using the minimum number of channels. The network has served and grown without interruption for nearly a century. New products and techniques have kept it up to date, always working. Today, the electronics revolution has transformed manufacturing. New kinds of challenges confront communications scientists and engineers. To make today's components, they must probe matter more deeply. To solve problems of material characteristics, to deal with temperatures from 200 degrees below to 2,000 degrees above zero Fahrenheit. They must create new materials and shape them on a molecular scale. This requires new tools, new processing techniques, an entirely new manufacturing environment. Precision is essential at every step in processing and measurement. Microscopes and instruments extend the capabilities of eyes and fingers, increasing skills. Atmosphere must be controlled, from tremendous pressures to a high vacuum previously found only in space. And dirt and dust must be excluded. Sometimes light and color must be controlled. From this new environment is now emerging the hardware of an important development in communications. Number 1, ESS, an electronic switching system. Designed by Bell Telephone Laboratories, ESS is manufactured by Western Electric for the Bell system to meet the challenge of expanding telephone needs. ESS represents a radical advance in making telephone connections. Virtually all electronic, it uses magnetically stored information to control the operations necessary to put through a call. An incoming call is detected by scanners, which report it to central control. Central control routes the number being called into a temporary memory unit, where it is held. Then, using the semi-permanent memory unit, central control determines whether the call is local or long distance, and what lines must be used to make connections. This information is contained in magnetized memory cards that function somewhat like punched cards used with business machines. The cards can be easily removed for alteration of the information. When central control has obtained all the data necessary for completing the call, it issues instructions to the switching network. The network, together with circuits that lead to trunk and local lines, performs the physical functions that connect the telephones. The time from the moment dialing is completed to the moment the called number rings is a small fraction of a second. ESS offers uniquely flexible, convenient service. It can transfer your calls to another phone when you're away from your own. If you're busy talking, it can automatically signal you that another call is trying to reach you. It can set up conference calls. And dialing just a few digits will connect you to numbers you call frequently. The key to these services is stored program control. Part of this control system is the semi-permanent memory unit, called a twistor module. In its manufacture and assembly, new processes and tools are being developed to assist human skills in achieving greater precision and uniformity. Access to information stored on the memory cards is provided by special twister wire. To make this wire, a thin permalloy tape is wrapped in a spiral around a small copper wire, thinner than hair, at 12,000 revolutions per minute. The tape itself is formed from wire under a pressure of 1 million pounds per square inch. Any dirt or imperfection in the metal, even a 10,000th of an inch in size, can ruin a complete memory unit. "45 twister wires, along with accompanying conductor wires, are embedded by heat between two mylar polyethylene belts. Wire placement is checked in the finished cable. During the early years of manufacture, electrical test records were kept on every 1,000th of an inch of twister wire, allowing a check on later performance. Here, as in most ESS manufacture, quality depends on precision. When the twister module is assembled, twister wires line up at right angles to copper straps, which function as solenoids. There are more than 300,000 intersections in each memory module. Not one wire can vary in position more than 3,000ths of an inch. A typical ESS program store includes 16 wired modules with a capacity of nearly 6 million information bits. More than half are used for self-checking maintenance programs. The rest used for more versatile switching programs than is possible with the electromechanical system still in general use. Another high production component, the sealed contact. This is the basic element of the ferried switch that performs line switching functions in ESS. Millions of such contacts will be needed every year. From preparation of the iron-nickel reeds to final assembly, mechanized processes are brought into play. There have been many production problems to solve. Not even a speck of dust 1,000th of an inch in size can be tolerated. Also, the reeds are soft after annealing. Human handling had to be avoided. The solution? Loading and transporting the reeds in racks through gold and silver plating to chemical and ultrasonic cleaning. A pair of reeds are sealed under pressure in a small glass capsule. Production problems must be solved every day. For example, unstable contact resistance. Its causes were not fully understood, especially in the early stage of manufacture. But the facts leading to a solution are coming from constant research and testing. ferried switch, which uses sealed contacts, represents a great advance in switching. When performance and economy become competitive, further advances will probably come from solid-state technology. Here is a world where material is grown into crystals with controlled impurities, with intolerances which are molecular, even atomic. The objective? Semiconductors, transistors, and diodes needed by the millions for ESS offices. Bell Laboratories' invention of the transistor and its later work in semiconductors made the basic concept of electronic switching a practicality. This single silicon crystal will be trimmed, then sliced and diced. These slices have been cleaned in a liquid by means of ultrasonic energy. A special technique, called epitaxial deposition, involves the growing of molecular layers in an oven to extend the originally grown crystal structure of the silicon slices. Control of temperature is critical. It must be uniform across the slices. Materials such as boron and phosphorus are diffused into the silicon to provide desired electronic characteristics. This diffusion is measured in parts per billion. Patterns are made by a photographic process and then micro-machined by chemical etching to produce nearly 1,700 transistors on each slice. Testing and measuring are continuous for resistivity, for thickness. These are controlled to rigid specifications to suit many applications. Hundreds of solid-state components nearly ready for cutting. New processing techniques are increasing semiconductor production rates as well as improving quality and reducing unit cost. As solid-state manufacture becomes increasingly sub-miniaturized, problems multiply. For example, in attaching leads. Gold wire, 1/1000th of an inch thick, is joined to thin aluminum electrodes that have a bonding area only a few thousandths of an inch square. Connections are made at a rate of 400 transistors per hour. Semiconductors must meet reliability and performance requirements matched only in missile and space technology. To assure uninterrupted service, major ESS units are duplicated in each installation. Alternate routing is accomplished in microseconds. There is a continuing challenge. Increase the production rate of ESS units to reduce costs and at the same time improve unit quality. The challenge can be met by improving design and manufacturing techniques. In the case of the ferried switch assembly, a newly developed concept makes it possible to wind 64 coils in one continuous operation. Mechanized processes such as this are expected to increase ESS frame production at a very rapid rate within the next decade. There are many specific manufacturing challenges. Operations such as wiring the ferrite memory module depend on human skills supplemented by training and expert supervision. Manufacturing a complex system is accomplished by dividing the process into many separate operations, such as this. Intricate yet compact circuits allow ESS to check itself continuously, report a change in component performance that may lead to failure, and direct replacement of a suspected unit. Faster switching and continual self-maintenance enable an ESS office to process many more calls than previous electromechanical systems, while requiring less space. Somewhat like a teaching machine, a wiring assist device uses punch tape, which causes a sequence of lights to direct the operator's work. In all areas of ESS manufacture, solving production problems has required a new look at the skills of people and machines, a search for the best ways to combine them. Human sensing, judging, and tactile abilities often provide a more suitable solution to a production problem and can be offered by the most complex machinery. ESS units are designed for a minimum of interconnections at the final installation, so that most of the wiring and much of the detailed testing can be done at the factory. Thus, manufacturing responsibility extends far beyond the making of parts to include integrated construction of an entire system. This manufacturing experience has already led to even more sophisticated processes and devices that may find application in future systems. One of the most promising developments, thin film circuits. In a unique moving line vacuum chamber, pure metal is deposited on glass or ceramic plates in a film only 4/millionths of an inch thick. Using an emulsion sensitive to ultraviolet light, photoresist processes generate circuit patterns. The negative design permits certain areas of the plate to be exposed. The pattern is varied according to the desired circuit application. The exposed area is etched off. Greatly magnified on a shadow graph, a resistor pattern is checked for precision. Each plate contains 54 complete resistors and interconnections. These thin film resistors can be adjusted to close tolerances. They're extremely stable and economical to manufacture. Contact areas for leads are deposited by a sputtering process. The basic goal, whatever the product, make it smaller, more reliable, more economical, extend its function. Beam lead and multiple chip circuits are a step toward fully integrated circuits grown into a single block of semiconductor materials. This is the threshold of electronic telephone switching. In the years ahead, electronic central offices will bring new and better kinds of service to the telephone user.
Hundreds of telephone buildings like this one, throughout the Bell system, house the automatic dial equipment that makes it possible for customers to dial their calls accurately and quickly. So quickly, in fact, that the bell rings almost as soon as the last digit is dialed. This accuracy and reliability did not just happen. No, indeed. It came of careful engineering, manufacturing to close tolerances, proper installation, and last, but by no means least, proper adjustment and care by telephone men who know their circuits and equipment thoroughly. Here we see a part of the dial equipment to take care of 20,000 customers. It represents an investment of about $2 million. In this particular city, the switching equipment is called step-by-step. It got its name because each call progresses through the office a step at a time as each digit is dialed. To telephone people, a knowledge of how this equipment works is basic to proper maintenance. Demonstration setup that we will use to show how a call progresses through a 5-digit step-by-step office. It is composed of 5 devices called switches. When the calling customer raises the receiver, a circuit is closed, starting the first switch, which is called the line finder. We'll do it again in a moment. Watch the line finder hunt the calling line. Also, watch the contacts of the line finder shaft, which we call wipers, step in to connect with the calling number's terminal. Now see it happen. The line finder is connected permanently to a first selector, which returns dial tone to the calling customer to tell him that the equipment is ready to receive the first digit. For this demonstration, we will dial the number 35286. The circuit is connected to contacts controlled by the telephone dial. As the dial is moved off normal for the digit 3, no action takes place in the first selector. But as the dial returns to normal, the selector will respond to the dial pulses. It stepped up to the third level, and by rotary action, cut in automatically to select an idle circuit to the next selector. This is the second selector. This switch will operate when the second digit is dialed. The next digit is 5. Again, nothing happens as the dial is rotated to the finger stop. But watch the second selector as the dial returns to normal. It stepped up to the 5th level as it responded to the second train of dial pulses and cut in automatically. The second selector extends the circuit to the third selector. This selector operates in the same manner when the next digit, digit 2, is dialed. The selector stepped up to the second level as the dial returned and cut in. The third selector extends the circuit to the connector switch. The connector operates somewhat differently from the selectors, as we shall see when we dial the first of the last 2 digits. The next digit to be dialed is 8. As the dial is moved to the finger stop, no action takes place in the connector. But when the finger is removed, the connector will respond to the dial pulses and step up to the 8th level. Notice, however, that it did not cut in. This is because it is now necessary to select the called party's terminal in the connector bank. The equipment waits for the final digit to be dialed. The 5th and last digit in this demonstration is 6. As the dial returns to normal, the connector rotates to the 6th terminal. The connector now sends ringing current out on the called line until the receiver is raised. Now let's watch another call as it progresses step by step through the demonstration equipment. If the number this subscriber is calling is in use, the connector will recognize the busy condition and will return busy tone to the calling customer. Let's see how one of the switches used in establishing this connection actually operates. The principles of operation of the first selector are basic to other step-by-step switches. It looks rather complex, so let's put it in a special stand where we can take a good look at it. Actually, it consists of 5 relays designated A, B, C, D, and E. Magnets and mechanical linkage step the shaft vertically. Magnets and linkage also rotate the shaft horizontally. A release magnet and armature release the shaft when the call is completed. This constitutes the mechanical part of the selector. The electrical part of the switch operation is shown in the circuit schematic. This tells a simple story to the experienced telephone man. In some cases, it is difficult to realize the effect of various adjustments on switch operation because of the speed with which it operates. The complete operation takes less than 1 second. However, with the Fastax camera, action can be slowed down as much as 200 times, so we can see just what does happen during switch operation. High-speed photographs like this one have been of great help to engineers in designing the equipment for long and accurate service. And of course, they are of particular interest to all maintenance people, for they serve to emphasize the importance of following the adjustment procedures outlined in the Bell system practices. The requirements in these practices have been carefully developed so that switches will operate with a minimum of wear and perform satisfactorily in spite of minor variations in customers' dial speed or their distance from the central office. Good design, a well-made product, and accurate adjustment mean good service.
The Place, a Pacific Telephone Central office in Glendale, California. One of the oldest functioning switches in the nation, a 35,000-line step-by-step office, is going to be transferred to an expanded ESS facility. Western Electric's speedy cutover service was selected by Pacific Telephone to provide a fast, reliable, and economical transition from the old to the new system. Features of the service are explained by Western Electric account representative Rick Snowden.
Speedy cutover service is a method by which installers come into the office to be transitioned from step or crossbar to ESS and actually perform the physical cut of the old office away from the new office. The out of service time is just a matter of seconds as compared to previous methods that took minutes and even up to an hour in some cases. Several installers come to the office maybe a month before the cut, and they analyze the cables to be cut and perform continuity tests to verify, to make sure that they have the exact cables and move them away from other existing equipment. After they're identified, they're tagged so that on the night of cut it can be a clean operation and nothing else gets cut.
For this cut, 127 feet of scaffolding has to be erected the day before to accommodate the installers cutting the cables on the upper portion of the intermediate distributing frame. On the evening of the cutover, 51 installers and 3 supervisors are assigned to cut the 927 cables. Western Electric supervisor Gary Brannon briefs them.
There's approximately 20 cables per person. These cable cutters are sharpened in a special manner so they will cut a clean cut through these and not cause any shorts.
Following a short rehearsal, the Western Electric installers wait with cutters ready. 3 floors above the IDF frame, Pacific Telephone people are hooked up to the cut supervisor and TSPS operator who is handling emergency calls.
I will be on that conference line approximately 1 minute before 11. They will give us the order to cut as soon as all emergency lines are down.
Mary Ellen, would you call the operator? Make sure there's no emergency calls in progress, please.
Hi, this is Mary Ellen at Glendale 11 CGO. Have we got any emergency calls in progress at this time? Good enough. It's all clear, Don.
Okay, Western, cut the cable.
Cut it! Let's cut it!
cut.
Nice cut, Western, 47 seconds.
Western Electric's speedy cutover service, an economical, dependable, quick response to telephone company needs.